You've been there, right? You're scrolling through the news and you get whiplash. One headline says this new food is a miracle cure, and the very next day it's a poison. You start to think, can science just make up its mind, please? So what is really going on behind all these conflicting headlines? Well, in this explainer, we're going to break it all down.
I mean, this is the core frustration, isn't it? Coffee, red wine, you name it. The list just goes on and on. And this constant back and forth isn't just confusing, it makes you want to ignore health advice altogether. But here's the thing. The reason for all this chaos isn't that science is broken. It's because we're often comparing apples and oranges. Or, in this case, two very different kinds of scientific studies.
So to solve this mystery, we need to meet the two main characters in this whole story of medical research. Let's start with the one you've probably heard of, the one everyone calls the gold standard.
This is the randomized controlled trial, or just RCT for short. Think of it like a perfectly clean laboratory experiment. Researchers take a big group of people and then, basically like flipping a coin, they randomly decide who gets the new drug or the new diet and who gets a placebo, a sugar pill, or just the standard treatment. The magic is in the randomizing. It washes out all the other little differences between the groups so you can really isolate the effect of that one treatment. It's designed to answer one question: can this treatment work under perfect ideal circumstances?
And then you have its counterpart, the observational study. And just like the name says, researchers, well, they just observe. They look at what's already happening out there in the big, messy, real world. Who's taking which drug? Who's eating a certain diet? Then they just track the outcomes over time. There's no random assignment here. People and their doctors are making their own choices. So this kind of study tells us how a treatment does work, in the real world with all its complications.
So it all boils down to this one single crucial difference: randomization. In an RCT, the researcher is in control. They assign who gets the treatment to create two groups that are as identical as possible. But in an observational study, the world is in control. People live their lives and the researcher just takes notes. This one little distinction, it's the source of pretty much all the debate and all the confusion.
And that debate, it often gets framed like a big battle. You've got the super clean, rigorous RCT on one side and the messy, real-world observational study on the other. And, common wisdom has a very clear favorite in this fight.
Yeah, the prevailing view is that RCTs give us the capital T truth. Their results are considered solid, reliable. Observational studies, on the other hand, are often seen as kind of flawed, full of bias, and probably going to be overturned by a better RCT that comes along later. It seems like a pretty simple hierarchy, right?
So this is the million-dollar question. If we take all the times that both of these types of studies have looked at the very same medical question, like does a certain statin improve survival, how often do their results actually point in different directions? Does the so-called gold standard always prove the messy studies wrong? The answer is, well, it's probably not what you think.
See, major scientific groups have actually put this to the test. They've done these huge reviews of all the evidence, kind of like a study of all the other studies. And what they found really turns the conventional wisdom on its head.
Check out this number, 1.08. This is the big reveal. A massive Cochrane review, which is itself the gold standard for this kind of analysis, compared results across tons of different topics. Now, they used a metric where a score of 1.0 would mean the two study types got the exact same answer. What they found was 1.08. That is shockingly close to perfect agreement, on average.
So when you average everything out from every study, there's surprisingly little systematic difference between what RCTs and observational studies find. It kind of seems like these two supposed enemies aren't really at war after all. But, and this is a big but, that's only when you look at the average. The real story, the one that causes all the confusing headlines, is in the details.
That key phrase in the last finding was on average. And as any statistician will tell you, an average can hide a whole lot of variation. Once we stop looking at that smooth average and we start looking at the individual head-to-head comparisons, a much, much messier picture starts to emerge.
Take a look at this.
A study in the Journal of the American Medical Association looked at 346 different drug questions where we had results from both RCTs and observational studies. What did they find? In nearly 38% of those cases, the two study types came to different conclusions about whether the drug actually worked. That's more than a third of the time.
So, wait a minute. How can the average be so close, but the individual disagreements be so common? It feels like a paradox. Well, this next chart, this is the key to the entire puzzle.
Okay, look closely at this chart. That straight line down the middle, that's the line of perfect agreement. If an RCT and an observational study got the exact same result, the dot for that comparison would be right on the line. As you can see, the dots do kind of cluster around the line. That's why the average is so close to 1.0. But look at how many dots are way off the line. Some are way above, meaning the RCT found a bigger effect. Some are way below, meaning the observational study found a bigger effect. The errors go in both directions and they pretty much cancel each other out. That's the secret. The average looks great, but for any single question, you could be way off in either direction. So what's causing all this mess? What's the gremlin in the machine that's behind all these frequent disagreements? Well, the primary culprit has a very specific name: confounding. This is the ghost in the machine of observational research.
Dr. Vinay Prasad uses this fantastic example to explain it. Some observational studies actually found that people who got a COVID vaccine were less likely to get into a car accident. Now, hold on. We all know there's no way a vaccine can biologically make you a better driver, right? That's impossible. So this acts as what's called a falsification test, an outcome you know shouldn't be linked. So what does the link reveal? Confounding. The people who chose to get vaccinated were on average just different in other ways. Maybe they were more cautious people in general. Maybe they drove less or had safer cars. The study wasn't really measuring the effect of the vaccine. It was measuring the effect of being the kind of person who gets a vaccine. That's confounding in a nutshell.
And this brings up a really subtle pressure. Dr. Prasad points out that in cancer research, observational studies often find this modest benefit, what they call a hazard ratio around 0.8. That number just means there's a small positive effect. But why that specific number, 0.8? He says it's because it's plausible. It's not so big that it seems unbelievable, but it's just big enough to be interesting and get published. This desire for a plausible result can actually subtly shape the findings of a study.
Okay, so if the average is misleading and individual studies can be all over the place because of this confounding thing, what are we supposed to do? How do we make sense of the next crazy health headline that pops up on our phone? Well, it really helps to remember that both of these study designs have their own unique strengths and weaknesses. RCTs are fantastic at killing bias and telling us if something can work. But they're incredibly expensive, they're slow, and they often test things in these perfect, almost unrealistic conditions. Observational studies are way cheaper, they're faster, and they tell us about how things work in the actual real world. But they carry that huge risk of confounding. They're really just two different tools for two very different jobs.
So here's the single most important thing to take away from all this. You have to reject that simple hierarchy. It is just not true that RCTs are always good and observational studies are always bad. A poorly designed, badly run RCT can be way more misleading than a super careful, meticulously designed observational study that does everything it can to account for confounding.
And that, right there, is the real secret. The label, whether it's an RCT or an observational study, is way less important than the quality. We have to become more critical consumers of this information. We have to start asking questions about how the study was actually done. Was it a big study? Were the groups they compared actually similar? Did the researchers even try to look for and adjust for confounding? So let's bring it all home. After everything we've just talked about, the next time you see one of those health headlines, what's the first question that should pop into your head?
You know, before you might have asked, was it an RCT or an observational study? But now you know there's a much better, much more powerful question to ask. And that is, was it a good study? That's the question. That's what cuts through all the noise and helps you actually make sense of the complicated but fascinating world of health science.